All right. Good morning, everyone. Today we'll continue with our lecture series on LLMs and tools. Today is going to be the last part where we'll cover how to build complex and more real-world applications using LLMs and tools together. So this particular topic is typically referred to as agentic workflow, and the agentic workflow is a very broad and sort of evolving topic. So there may be multiple interpretations of agentic workflow. But today I'll be discussing what I understood from the literature that's out now. So before jumping into the actual content, let's sort of think how do we typically do real-world complex tasks, right? So here I've taken two different tasks. One is a simple programming assignment, and two is writing a research paper, right? So typically, how do you go, given that you have a programming assignment? Maybe the lecturer covered the professor covered the topic at hand, and the TA has given you the problem. So how do you go about from the time you get the assignment till the time you submit the assignment? Probably, maybe you can describe like the broad steps that you do, right? Like typically, okay, maybe you can differentiate how an LLM would work, right? So how would an LLM work? If you give it the problem statement, it's going to give you the response right away, and that's it. It will, if LLM is a student, it will submit the assignment. Is that what you would also be going through? So what would be the difference? Yes, you think about it a lot, divide it into steps. That's a good first step. And would you tackle all of them together, or makes sense? So one strategy is that you divide it into multiple subtasks, and then you figure out how each of the subtasks is dependent on each other, and then figure out a strategy on how to solve it, right? So now let's say your module 2, which you are supposed to do, is not working as expected. So would you go ahead with module 3? You start debugging. Yes. And how do you start debugging? So if you have any doubts, you would ask somebody who is an expert in the field, or probably if an error is thrown, then you would browse the internet and then figure out, or maybe you can even ask other experts in the group who are your classmates who might have already crossed the second module, right? So this doesn't seem like what LLMs typically do, right? It seems way different than what they do. And so I'm not sure how many people have gone through the process of writing a research paper, but like one of the biggest hurdles in writing a research paper is that you won't know whether you did a good job or not until somebody else or the reviewers comment on it, right? And that's an extremely long cycle, right? Even though like the cycle in your programming assignments is quite quick. You get the observation quickly, then you figure out what to do. You then go back, change your code, change your strategy, and do things, right? But writing research paper, again, it has multiple hierarchies. Like maybe once you write your introduction, you will change the way in which you pitch the problem, and then so you write your experiments accordingly. And then if that experiments are not coming out right, then again you will go back, change your introduction to make sure that it fits the story that you can say with your experiments. It's a very complicated cycle where it's just not like I give you the input and then you end up getting the output, right? So almost all real world applications are of this type, right? The main reason is being that you're not the only actor in that process, right? So if you have to pay your college fees, it may so happen that the portal is not working. It's not in your control, right? It may so happen that the administrative department has changed the fee structure and they have not informed you about it. Maybe you missed the email. So there are a lot of actors involved in solving a task at hand. So it's just not that you get the entire problem description in one go and you have the ability to solve it in one shot, right? And if you have to use LLMs for real world applications, they should be also in a position or they have to provide you a way in which LLMs can work in the same way that humans work, right? So that's going to be what we're going to cover in this lecture, and this is called an agentic flow, right? So let's first differentiate between a non-agentic flow and agentic flow so that the difference is quite clear. As we discussed now, typically all the LLMs, they go from start to finish in one direction and then they give you the answer, right? So for example here, most likely when you're in 12th class or in 10th class and you have to write an essay in your answer script, while you do that process in your head, similar to how LLMs would do it in multiple layers of its transformer architecture and arrive at the answer finally, and it would spit out one word at a time. We also did the exact same thing, right? We would just, whatever we have to say, we'll just think about it, and then we'll start writing one word at a time and then finish the essay. So that is non-agentic flow. But writing a research paper is sort of similar to writing an essay, but we don't do it that way, right? Write a rough draft, maybe write an outline, then move ahead, write something else which is for which you have the results already, or you know that it's going to be there for sure, like related works or things like that. And then so there is going to be a lot of back and forth. So one such example here is that if you want to write an essay on topic X, then you'll probably go do search on the web, figure out what all topics are there, and then maybe jot down some notes which you can keep handy later on. And then you write a first draft and then revise, you can also get your draft proofread by somebody who can give you more suggestions. So there are a lot of things that you can do. And agentic workflow is where you spend a lot more time in iteratively fine-tuning either the entire solution or like mentioned in the first example, like it's divided into multiple parts, iteratively do each part until you succeed because there's a dependency, and then slowly move forward, right? So this is what is agentic workflow. So let's look at an example here, right? So this is from a lecture by Andrew Ng. So here there is this benchmark called human eval. This is basically a coding benchmark where you are given the problem statement and some description about the problem, and you'll have to end up coding the rest of the meat of the entire function, right? That's the task here. And typically how GPT 3.5 or GPT 4 would do is, like, if you give it the description and an empty function block, it would fill up that function and then give it to you, right? And the good part about this human eval benchmark is that it's measurable. Like, people who define these benchmarks have written like 7 or 8 unit test cases per function, so that once GPT 3.5 or any LLM writes the code for that block, you can execute that in a very safe environment and then get the results to see if it actually cleared all the unit test cases or not, right? And if a particular output clears all the test cases, then it's considered to be successful, right? So what they show here is that on the human eval benchmark, GPT 3.5 gets a zero-shot accuracy of around 42-43%, right? And GPT 4 is miles ahead, right? Which is at 66-67%, right? Which is almost like a very big 20-point jump, right? Given that it's already only at 40. But these ones that are in blue, orange, and red are agentic workflows, right? These are not one shot. These are agentic workflows where you get a solution, and then if you're not happy with it, you have access to your unit tests, you run your unit tests, you figure out where the module fails, right? Feed that back into the system, and then iteratively refine your solution until you get to a point where it's reasonable, right? So this particular slide that Andrew presented sort of emphasizes the importance of agentic, or the power of agentic workflow. So what they say here is that the boost that you get from GPT 3 to GPT 4, you would get a lot more boost if you just use GPT 3 in an agentic flow, right? It's just that you'll have to spend a lot more money in getting the output, because you might have to call the LLM 5-6 times, and the context might be pretty long. But you have, if the task demands it, you can actually solve it much better with an agentic workflow, and you don't have to wait necessarily for the next version of the open or the LLMs to come out to sort of solve your task, right? So that's the crux of this, and in this lecture we'll be talking about how you would design or how would you end up using something like GPT 3.5 or 4 in an agentic fashion, right? So you, like, there is always this thought, right? Like, already LLMs are extremely expensive, right? And now like, people are saying iteratively use that, you will get better solution. Now if you iteratively use that, you're going to end up spending 5 times 6 times more money than what you would spend, right? Then the question comes, is it even really worth it, right? Are you really going to get any benefit by spending so much money, right? Turns out that there are some cases where you can actually make money, right? So one such example is there are a lot of engineers who keep track of their GitHub repos, and once somebody creates an issue in the GitHub repo, they'll have to work on it to figure out whether it's indeed a bug or not. And if it's a bug, they would reproduce the bug, and after they reproduce the bug, they'll work on a solution and make sure that it doesn't break the existing system, patch it up, and then release it, right? And this is an extremely time consuming cycle. So for some simple bugs, you may take 2 days. For some really complicated bugs, you might end up taking a week, right? And the amount of money you would spend on a software engineer is a lot higher. And the amount of time that he spends or she spends is also a lot higher, right? So now it sort of feels like there are some cases where you would actually save money by using agentic workflows rather than simply calling the LLM ones. Because if you're not able to fix a bug and you're always going to get suboptimal solutions, let's say you're only going to get your issues fixed 5% of the times, right? Then spending so much money doesn't seem right, right? But if there is a huge jump because of this agentic workflow solution that you have, and from 10% you can solve like 40% of your GitHub issues, then that's a very good jump, right? Of course, you're not with the current state of the art, we are not saying that you would be able to solve everything. That's anyway going to be really impossible, but 40% is still a big number, and it would end up saving a lot of money, right? Now, it's not just software engineering, right? There is a huge list of software support that people do. Like, let's assume that you have a cloud instance running. Like, let's say you manage Amazon Web Services or IBM Cloud or Azure, right? There's going to be so many system failures. There are going to be insane amount of logs, right? And if a system fails and if something is not up, then the site engineer would get a mail saying something is down, and then they'll have to go through insane amount of logs and figure out what is wrong and then try to come up with a solution, right? Imagine you can automate some things like that, right? That's going to end up saving a lot of money, right? Because you don't have to wait for the engineer to be available to look at the logs and things like that. So there are a lot of these applications where, because the turnaround time anyway is going to take a long time with a human involved, maybe using an agentic flow can help benefit, right? So that's the sort of goal of why people are after agentic workflow, and that's why the notion of complex tasks comes into picture, right? So in this lecture, we're going to talk about like 4 important papers in this particular field. These are very recent papers, and they have insane amount of citations because of how applicable they are, right? Okay, so let's talk. So before going into the exact algorithm, let's talk about one of the data sets called Hotpot QA. This is a very commonly used data set for most of these frameworks to study. The reason why this is an important data set is because typically when you have a document grounded QA system, you would use a retriever, query your corpus, you get the documents, and very likely these documents are going to contain the response, right? So these are typically called single hop reasoning. You have the question, and if you search with the keywords in the question, you will end up hitting the document which has the answer, right? But that's not always the case, right? So let's take an example here. The question is, to what team was the 2014 NBA Rookie of the Year traded in October 2016, right? So here, if you search for the keywords 2014 NBA Rookie of the Year, then that would get you a document which would contain the name of the Rookie of the Year, right? So once you have the name, you'll again have to figure out who this person was traded to in October 2016. So this is a 2-hop reasoning question, right? You can have multiple hop reasoning as well. Like, for example, if you have a Wikipedia page for each cricketer, then if the question is, can you give me names of 4 cricketers who were from Mumbai, right? So then if there is no single document that talks about all the cricketers in Mumbai, then you probably have to go through each cricketer's page, figure out whether they are from Mumbai or not, and then club them together and write, right? But this is not a multi-hop query, but rather it requires inferencing from multiple documents, right? So here in the first paragraph, you will be able to figure out that Tony Shell traded Tony Shell to Milwaukee Bucks for Michael Carter Williams on 2016. So this document contains the second part of the answer, which talks about who was traded in 2016. And this particular paragraph talks about that the NBA Rookie of the Year was Michael Carter Williams, and this particular sentence expresses that, right? So this is a really good use case to study how different ways of agentic workflows fare, right? Because it doesn't seem like in one shot you'll be able to get what you want unless your LLMs already have memorized the whole thing, right? Of course, if the language models have memorized the whole thing, then you can get it, right? If not, then this task is a good task to figure out how it works. There are also other tasks that people use. For example, there is a real world like sort of simulation game wherein it says that you are entering the room and there are 5 objects here, okay, and your goal is to put the salt and pepper shaker into the sink. But when you enter the room, you won't be able to see salt and pepper shaker anywhere, because the list of things that are given to you will be like cabinet 1, cabinet 2, drawer 1, drawer 2, table, sink, right? So you'll have to use a little bit of common sense and then say like, let me open drawer 1 and check, or let me open cabinet 1 and check. And then once you open cabinet 1, then an observation would come saying like there are 3 plates and 2 tablespoons in this particular cabinet. So then you say close the cabinet, then open drawer 2. So you'll have to use a bit of common sense and also keep track of what all you did in the past to sort of finally be able to solve this problem of finding the salt and pepper shaker and keeping it inside the sink, right? So this is another sort of a simulated game that people use to test whether these agentic systems, how good or bad they are, right? Because they're combining both reasoning and the ability of LLM to keep track of things, a multi-hop, how they can agentically, how they can iteratively sort of solve this, right? So one such example of a hotpot QA question is that aside from Apple Remote, what other device can control the program Apple Remote was originally designed to interact with? So first we need to figure out what is that program that Apple Remote was originally intended to interact with, and then we have to find what are the ways in which people can interact with that particular program, and then figure out the alternate, right? So if you use an LLM and then just ask it to answer, then here it says iPod, right? And of course it's not the right answer. Yes, so it's mostly because there are so many terms about Apple, the most likely answer was iPod at that point in time for the model, right? And now you can also use chain of thought reasoning, because these LLMs sort of know a lot of things about the world, and maybe if you ask it to reason, it may arrive at the right solution, right? So here again, it says that Apple was originally designed to interact with Apple TV, and Apple TV can be controlled by iPhone, iPad, and iPod Touch, which seems right. If Apple Remote was first designed to interact with Apple TV, right? But it was not. So Apple TV was not the device for which Apple Remote was originally designed to interact with, but it was one of the products that it could interact with. So again, this is this answer made an assumption, even though the chain of thought seems valid, because it doesn't say was the, so in other than this part, everything else sort of is right? Because Apple Remote can interact with Apple TV and everything else is true. So except for those 2 words, everything seems to add up, but there's a bit of hallucination there. But it seems very plausible for a person who doesn't know the thing, right? So now let's say that you have a corpus of all these documents, and then give it, let's say, wiki search or document search or one such tool, right? So then, like we saw in WebGPT last time, right? If you have the corpus at hand, then you can and you have a lot of actions that you can do, like search, go to the next page, go back to the search results, reframe the search query. You have a lot of actions in your disposal, and if you use things like that, you may get to the right answer, right? Because WebGPT gets better answers than the other techniques, right? So it's bound to be better. So here, after it did a couple of searches, it was actually able to figure out that Front Row is the right software, right? Front Row is sort of like is a software within the Mac OS, which lets you play media, play photos and things like that, and you can control it with a remote, right? And so then it searched for Front Row, and it was not able to figure out the right application, and so it searched for Front Row software, and it was able to get something, but finally its reasoning was not right. It said answer is yes, right? Which doesn't seem like a plausible answer for the question at hand. So until here, people have already worked on, right? People have a web GPT solution which does act. If you have a set of tools and you have a set of actions you can perform on the tool, how do you integrate it into the LLM workflow? That's already there. So the new thing that sort of was introduced is just to combine COT and act only together. So all they're saying is like, once you get an observation back from the action that you did, then just think about it. That's all they're saying, right? So here, the thought after the first search result is Apple Remote was originally designed to control the front row media center program. And then it says, I need to search for front row next and find what other device can control it. So far it's right? So then it searched for front row, and then it got some output from Wikipedia, and then it says front row is not found. I need to search for front row software, right? And then, so until here, even Act got it right. And then the final thought was front row software is controlled by Apple Remote or keyboard function keys. So the answer is keyboard function keys, right? So the only, like, the novelty here is just combining COT and Act together. That's about it, right? So this sort of, this notion of making the model reflect on what it observed from the outside environment was actually crucial, right? So this seems, in an inference state, this feels like RL, right? Like you do a certain action, like typically RL agents are trained this way. You interact with the real environment, and once the environment gives you something, then use the observation, and then you use that to get back. In some sense, Act also is like that, right? So Act and React fall under the same bucket of looking at them as like agents which interact with an environment. But the only difference here is that, I mean, the even though it appears obvious when we say that let's mix COT and Act only together, but it's not so obvious. The reason being that typically machine learning scientists or so who work in RL typically, right? They have this fixed mind that action space has to be discrete, right? And if you have a really open space for actions, you're never going to converge, right? So here what we're saying is that this thought and action are now the new action space for us, right? So you have a discrete action space for searching and looking up, and then you have almost a countably infinitely large language action space, right? So this, like, so that's why it doesn't naturally come to people who work in this domain. But the good part here is that at this point in time, the large language models were so good, right, that you don't have to cold start, in the sense that you don't have to start from a policy that doesn't know anything, right? If you give a couple of examples or 3 examples in the context, then it would give you an action that almost has good, like really good non-zero rewards, right? So it's only because of how good the LLM is that this technique would work. The LLMs are not good, this is bound to fail, right? Because you're just feeding it, you're just giving it very little clue, and you're giving it so much input, it's not going to figure out what to do with that much information without proper guidance, right? Right. So like I said, yeah, so it's an extremely large language space, and so like very strong priors are needed. So that's why this particular paper had to wait until you have something like GPT 3.5 or GPT 4, right? Because otherwise, even if you had this idea, you would have not been able to get good results with it, right? So here what they say is that, so you guys already know standard prompting, which is like, given the input, just give me the output. You already know COT as well. You reason through and then arrive at the answer. So there was also like a follow-up paper of chain of thought that was called self-consistency. So it's a simple extension on top of chain of thought. All it says is that rather than doing greedy decode, sample, let's say 21 or 25 outputs and do majority voting or some type of marginalization, and figure out the one that has higher likelihood of being the answer, right? So that simple technique sort of boosted the accuracy from 29 to 33. And then these guys also implemented Act and React on top of Hotpot QA. But as you can clearly see that it is worse than COT. in this particular setup, right? This is just 27, and even standard output seems a lot better, right? So now again they dig deep into figuring out like why did this didn't work, right? Because they had all their theories, right? They're like, okay, it would not have worked if GPT-4 or GPT 3.5 was not there. Now we have GPT-4, GPT 3.5, it's still not working, right? Or should we wait for more, or is there something that's happening that we don't know underneath, right? So basically what they figured out was that the source of failure for React and COT are different. Okay, so like you saw in the previous example, COT gives you a really plausible answer here, even though its chain of thought is incorrect. Many a times, the chain of thought is not right, but still it arrives at the right answer, right? Whereas React, on the other hand, unless it has evidence, it cannot move ahead, because it's sort of programmed in a way that if you're not getting through to what you want, then try different acts and then arrive at the solution. This is like, if you don't solve the second component in your assignment, then you are stuck in the second component until you solve it, right? But many a times that's not the right strategy, right? You probably would get very partial marks in your assignment. It's better to code the whole thing and then say that this module failed. You will probably end up getting better marks than just working lot more than on that particular module, and still you won't be able to convince your TA, right? That you spent a lot more, or you didn't do the end-to-end thing and things like that. So there were some pros and cons for each of them, and so they decided like, let's combine them together and see how it goes, right? So they knew that at this point in time, the chain of thought with self-consistency is doing like really good, right? And can we combine that with React and then see if there is any pros and cons? So basically in chain of thought self-consistency, what happens? You will have to marginalize after you get like a large set of outputs. So then there may be some ties sometimes, right? Or maybe the top output and the second top output may not be that far away from each other, right? So what they say is like, first let me do COT self-consistency. I'll apply some rules on the marginalized distribution, and if that rules clearly says that COT SE is the winner, then I'll use that output. If not, I'll resort to React, right? Similarly with React, the other approach was that first you do React and then you do COT SE. So what they did there was, React typically goes through this iterative step, right? So let's let it go for 5 or 6 steps. If it doesn't get me the final answer by 5 or 6 steps, then I'll resort to COT SE, right? So when they did these two things, they were able to see that both these techniques were able to outperform COT SE on this data set, right? So what this sort of table shows is that even if you don't see improvements over COT SE, still this particular framework has the potential to help you increase your accuracy. Right? So it depends on the problem at hand, basically. So you'll have to analyze the problem at hand, figure out the source of failure, and the source of failure will help you understand whether it's good to mix this with some other strategy or it does work on itself better and things like that. And again, chain of thought can only be used in scenarios where the LLM understands your domain, right? So hotpot QA is something Wikipedia is present in, is something that can be solved with the knowledge that you get from Wikipedia. So you can use COT self-consistency, but not like, it's not that you can use chain of thought for all the tasks that you have, right? So there are some limitations of what you can achieve with chain of thought, but React is sort of like a very open framework which can let you do a lot more than this, and that's why the other tasks in this paper clearly tells you that how they are better than the best baselines in their particular field. Like the ALF world example that I gave you, there are a bunch of other examples as well, where, data sets as well, where they show that in symbolic logical reasoning and things like that, React is much better, right? So the other thing to sort of see here is that one way to sort of do all these techniques is by feeding few short examples in your prompt and then asking the model to follow that framework, right? And the other technique is like in the previous lecture we talked about function calling, and where we discussed how do you synthesize data, right? Without human intervention, how can you synthesize data and if you use some sort of an iterative technique to synthesize a lot more data and then use it to fine tune, what they say is like a smaller model fine tuned with React or Act will be able to surpass a very large model with any technique, right? So this is a cost saving technique, right? Because you're generating data also for free. You don't have to necessarily annotate the React framework in your examples. If you have the tools at hand, and if you have a data set that just gives you input and output, you can actually simulate the React framework, figure out which subset you want to use for fine tune them without human intervention. And when you do that, you end up getting a fine-tuned model for your task, which is better than using a 540 billion model, right? So this is actually a really good insight from this paper, that React is a good framework to work on. So, in the first example that I gave about like where would you use agentic workflow, I talked about the SWE agent. So this is a software engineering agent where the environment here is like what a software engineer would interact with on a day-to-day basis. You have repos, you have a lot of tools with you, with which you can code, execute, see the output, figure out what is not right. You might have the GitHub repo with you where people have commented about what issues they faced and what somebody else tried to do and what they couldn't reproduce. So you have a lot of information there. That's the same sort of environment the SWE agent would also work, right? It has access to all the files, right, in your particular repo, and it also has access to the a place where you can edit those files and also execute a program. So the main the SWE agent uses React, right? They use this framework to sort of provide a solution for this, and that solution, so the best solution before that was RAG, which sort of only solved 10% of the data in SWE bench, but the SWE agent which used React was able to solve more than 20%, right? It's still a long way to go, but 10 to 20% is still a big jump, right? And the main contribution of this paper was that how, rather than just giving it anything and everything under the world, like anything and everything under what Linux shell could do, like that was initially what people assumed, right? But then here they gave a very small subset of those commands, and which also take into account how much data you can fit in the prompt. Like rather than giving the entire code base, you can give it some tools to sort of localize some part of the code base that can be of interest to you. If it is not of interest, disregard them from your prompt, put something else, so that you save the space, make reasoning over a smaller amount of data, and make the task slightly more tractable than what it was before. So they do a lot of these mostly software engineering related things, but that gives you insane boost in numbers. So the two contributions here are like use React, and sort of if you have your task well defined, then hand engineer your tools that you're going to give the model rather than giving them very open tools, right? So what they say is that you have a bunch of in context examples along with the system instruction. System instruction tells you what SWE agent is supposed to do, right? And you have a few short examples here, and then you give the current issue, which is what was a reported issue, and some information about how you can solve this. If you're like an architect, you can probably give that to your developer by saying maybe look into these things, right? And then it follows through this whole process of thought, action, and observation, thought, action, observation, and then finally gives you a patch with which you can create a PR, right? So some examples of actions and responses are open this file name. So rather than opening the entire file, it will tell you that I'm opening this part of the file where there are 255 more lines on top. This is the file that I've given you, and there are some more lines in the bottom. Now you decide whether you want to scroll up or scroll down, right? And there are some other things like find file, search in a directory, and things like that. So once you localized where you want to fix, maybe 3 or 4 places in your code repo, you feel like if you fix it will get you the right output, then you think about it first, which is the thought part of React. Here it says like we need to add a check to ensure that all powers are the same. Let's edit the code to include this check. So it figures out that there is a specific edit command that they've given access to this particular SWE agent. It tells you which line numbers it's editing and the exact code that has to be replaced, right? So they've made it very, the output space to be very small, so that the model can focus on what is the right thing to be done rather than figuring out from a whole set of big noise what is the right thing to be done, right? So this is the sort of idea of React and how React gets used in multiple agentic solutions. You can also have a RAG-based React for hotpot QA. So you can do a lot of things with React, right? Now, another sort of good idea that people had in parallel to React was called self-refine. So this again, the only common link between self-refine and React is that you go iteratively, right? But the iteration here is slightly different. They don't go through the steps one by one and then figure out what tools to use, what prompts to use and things like that. But all it says is like, okay, you generate the output however you want. Okay, you use direct prompting, you use chain of thought, you use chain of thought consistency, self-consistency, you can even use React, but you arrive at the solution. Now, once you arrive at the solution, just look at the solution and the question and then tell me whether you as an LLM think this is right. That's all, right? That's the only that's the only idea of this particular paper. This is very simple, but it's very effective, right? So all it does is like once the input comes, it sort of figures out, gets the output first, or if it already has an output, it refines the output and then gives it back to the feedback module, which gives, with the feedback would also be in mostly in natural language, right? And then based on that output, you end up refining again until the feedback module or the judge is happy with it, right? Now, where all can this be used, right? So let's say that you're creating a chatbot for IIT Delhi, right? LLMs may not have as much filters as what you want, or they may not be able to follow very fine-grained instructions you give. Let's say if you give 50, 60 instructions, it's bound to miss out a few instructions, right? So, and one way is that you let the LLM generate the response, and then you have a list of instructions with you. Check whether each of these instructions individually is making sense or not, or group some of these instructions together where LLMs commonly fail, and then in your feedback just check for those subset. So you can do a lot more things after you get the output, and once you get the output, then you tell the language model like, look, this part is, I'm not very happy with this particular output, so just modify that part and I should be good. So then that becomes a lot more easier for the LLM to follow. Right? The same as talking to a child, right? If you give the child like 20,000 instructions, is bound to forget a lot of instructions, right? But when they are doing it, you give them reward, you give them like feedback on a very specific thing, then they're more likely to follow it, right? So that's sort of the crux here. So here, if you see in one of the dialogues, it says, I'm interested in playing table tennis, and the response here is, I'm sure it's a great way to socialize, stay active, right? It seems slightly unhinged. So here, the feedback is that you're not providing any information about table tennis, so it looks like you don't understand table tennis, right? Because you could say this answer for almost anything the user says, any activity the user says. So then based on this output, it sort of realized like, that's great to hear. It's a fun sport requiring quick reflexes and good hand-eye coordination. Have you played before, or are you looking to learn? Like, this is slightly better, even though it can be applied to any sport, but still, first round of refinement at least makes some sense, right? But this has a lot more use in code optimization, right? So here, while you're not running the code, like in case of SWE bench or SWE, you create a SWE agent, or if you have access to some of these human eval coding data sets, you can run them, verify on the unit test cases and figure out whether it works or it doesn't work, right? But let's say you're looking for something like space complexity or time complexity and things like that, which the LLMs typically know a lot, right? So here, once you make the LLM write code for your use case, you can have a prompt in your feedback that specifically asks a model to discuss the complexity, right? So here, while that was not your criteria to begin with, right? So this code is slow because it uses brute force, and a better formulation to count sum until an integer n is just to directly use this formula, right? So this can help the model refine its output based on the feedback that you give, right? So typically your evaluation criteria becomes your feedback, right? You will always have an evaluation criteria to, if you have a data set, right? So then that could help you get sort of incorporate that back into the loop and then use this to make your output better, right? So this self-refine is sort of like a prompting strategy, right? You have a lot of different prompting strategies. This is like, in addition to getting the output, just refine it with a different prompt and then see how it sort of iterates. So on a lot of data sets, there was an insane boost in self-refine, right? So in self-refine, the good part is that you don't have to worry about what the base prompting strategy is. Your base prompting strategy could be COTSE, which is doing incredibly good. Now you're writing a wrapper on top of it, right? So it is sort of like a complementary technique, which is why this paper is very important, right? So React is sort of like is of the same type. Right? You have to replace React with chain of thought self-consistency. If that's already doing good, then they're trying to figure out how can we best leverage both together and make all of them work together. But here it's completely complementary, right? You can sort of use it with anything. And that's why you see, like in almost all cases, there is either it maintains the same amount of performance, because typically the feedback comes back and then says, I don't know what to do after this. Like, because the LLM did what it can do the best, and the feedback model is just not giving any valuable feedback back to the LLM where it can correct, because it's the same LLM that's trying to correct itself, right? So the model is done. So if you see one of the math reasoning tasks, it's done. Like, it's not giving out. But the good thing is, it's not losing out, right? So this is really important. And there are like incredible jumps in certain metrics for dialogue response generation, code optimization, right? So there's a good jump for GPT 3.5, and even GPT-4, which is miles ahead of GPT 3.5, also sees improvement because of this agentic workflow, right? And this was what Andrew Ng was discussing in one of his early videos on why agentic is very important. Do you guys agree that discrimination is an easier task than generation, right? So even if I give you the same instruction and I tell you just verify if this is right or not, or I tell you give me a solution for this, do you think the accuracy of retriever or the discriminator would be much higher than the accuracy of the generator, right? So that is one reason why this strategy works. Second thing is that typically you have 5 or 6 constraints in the system instructions, or you have a detailed system instruction for how this task is to be done when you prompt it, right? But in case of feedback, you can have very specific feedback about the place where LLMs are currently not doing a good job. Right? If most of your failure is coming from a certain specific error case, right? Like how they analyze the React and the self-consistency frameworks. They mentioned that one can hallucinate a lot but arrive at the right answer. Other, once it cannot find a right path, it will get stuck there. So if you have these task-specific intuitions, then you can easily incorporate them into the feedback, because you know that model gets confused there, and I just have to hint it to do the right thing at that point in time, right? So some amount of domain-specific expertise where exactly what you give in the system, in the prompt for response generation and the prompt for feedback are slightly different. That will help. And secondly, discrimination is always easier, right? And there are a lot more like reasons for it, but these are the main 2 reasons, right? So one other reason is like feedbacks are multi-dimensioned as well. Like let's say that you have 5 different dimensions for dialogue, like coherence, relevance, engagingness. You have multiple different dimensions. You can score the model in each of these dimensions and then say you're only getting 20 out of 25. Make sure that you get 23. So the model will keep generating until it hits 25. So, okay. So the summary here is that React was an alternative for chain of thought. It does reasoning and act together. That was the intuition. That was the novelty there. In self-refine, you iteratively sort of improve the initial results the model gave using feedback. And the good part was it can be combined with React, right? So it's a lot more powerful. So let's take code optimization, right? So what you would typically say is that write a code for doing a certain thing. And in addition to that, you would say also make sure that the code is well optimized, right? So now it is not a guarantee that it would follow both, right? But when you're evaluating, you're not really checking the first part because you assume it's right. So now the instruction that you give is a lot more precise, and in some cases, based on what you've given in the few short examples, you might have given clear instructions for what typical cases you would say, and how you would phrase that feedback, right? So these phrasings typically you cannot incorporate it during code optimization in general because it may not fit very clearly there. But in case of reflection, some things fit a lot more clearly than what you could do it with the initial prompt. And also again, the other insight is that typically people know where it fails, right? So like maybe the cases where Llama would fail may not be the same case where ChatGPT would fail. Maybe where a very small model would fail may not be the case where a large model would fail. So just for the same instruction, you can actually end up having different feedback prompts, right? So error analysis is very important to figure out what type of evaluation metric should you use for feedback and what type of thought you should give, because the thought that you put into the feedback generation cycle has to be understood by the model inherently, right? If it cannot put it back, so it requires a lot of effort to figure out what is the right feedback and how that feedback can be made usable. So most of these, the framework is what like comes out of these research works, but if you have to make it work for your project, you will have to put in a lot of effort. It's not going to be like very easy to get it to work. Okay. So let's move on to a slight extension of self-refine, right? So it's a combination of self-refine with tools, right? So typically self-refine, the crux was that you just have to use the same LLM to give you feedback. But all this paper is saying is that don't be biased by just using LLMs. Use a different evaluation metric, right? If you are running code, then use the code execution results to bootstrap. If you have an interpreter with you, if you have a syntax checker with you, run the code. If there's a syntax error, feed it back into the system, right? So that's sort of like the main contribution here. And then what they say is that once you get the output of that module out, then reflect on that module and then feed it back. So basically the output of the system is fed into a tool. Maybe it could be a heuristic tool, it could be a test cases, it could be a binary reward. Get the reward out and now do reflection on top of the output, the trajectory you've taken so far and the task, right? So they just removed the entangled two parts together. So in the previous work, which is self-refined, they just said the evaluator and the feedback generated sort of extremely coupled together. So you don't even see what the evaluation happened, you just get out the feedback, right? So here they're saying just decouple them, then you can use anything you want, right? This becomes a lot more useful in a practical sense. And so basically the only difference here is that after you get, so once a user request goes in, right, LLM gives you a response, and then you have tools, right? You can end up using tools, right? Once you do your tools, then go to an LLM, which again will use the output of the tool and everything to figure out what the feedback should be. Again, give it back, create a new version of the output, give it back to the tool, and then keep iterating over this. And finally, once you're happy, give it back, right? So the only difference here is that before this whole block was just the LLM, and it would give a revised thing back. Here, it's now an executor and an LLM side by side, right? And this simple decoupling, right, gave a lot of boost. So basically, what they found is like in hotpot QA, once the model fails, it never could recover, right? That was the biggest issue there. So now, because of this new small thing added to it, it was able to recover. Let me show you an example, right? So here, so again, if you see here, the good part here is like this whole pipeline could be React, right? This whole pipeline could be React, right? It's not a replacement for React, but it's a replacement for self-refine, right? So just like how you could use React and self-refine together, you can also use React and Reflexion together, right? So here there's one example here. Here there's a question that says, grown-ups starred the actor who was best known for which role on a TV show, right? This was the question at hand. So the first action it did was search for the TV show grown-ups. It got the right document. It figured out that it stars these many people, right? Now the second step is just to figure out which of these people starred in this TV show Hello Hello and what their character name is. Again, it may require 2 more hops. This may be a 3-hop question, but let's see how it goes, right? So then once it figured out these are the character names, then the second thought it had, once it had this result, is like, grown up stars these many people, I need to search Hello Hello and find which actor was best known for which role, right? So it's going to say search for the other TV show. Now it searched for the other TV show, but it did not yield anything that matches with this particular setup. If it would have also given you a list of actors, you would have just done an intersection and figured out which actors are there and find the role of that person, right? But that didn't happen. So finally the model came out and then said Rene Artois is a right answer, right? But it's not. So then now here is where the observation comes into picture. Here the observation says that the answer is incorrect, right? And now an LLM is reflecting on it, saying, I searched the wrong title for the show, which resulted in no results. I should have searched the show's main characters to find the role he was best known for in the show. So basically that TV show does not have entries, or it does not have enough information within that article which can give you a lot more information. So the alternate sort of way to go about is like start searching for each actor's names and see if there is a mention of Hello Hello and the character there in their particular Wikipedia page or something like that, right? So that's what the second round did, where it knows that it's not good to search for Hello Hello because the previous iteration did that and made that mistake. So now it directly searched for one of the actors, Sam Kelly, and now in the Sam Kelly page, it clearly said that he is best known for his role as Captain Hans Green in Hello Hello, right? So now by not going through like each TV show at a time, finding the intersection and then figuring out, it's figured out that going that path is not going to give me good results. So if I go through that, it's going to end up, I'm not going to fix it, right? I'm going to go in a circle where I'm not going to get out of it until I find the right one. So I will not take that route, rather I'll take a different route, right? So this notion of where it failed before is now incorporated into the whole reasoning cycle. And that actually helps it recover from that plateau of where it got stuck in the previous paper, right? So again, there are a lot of these coding tasks. Human eval again is a coding task that I mentioned earlier. One is on Python, other is on Rust. There is also I think the name is most basic Python programming something, right? It's also a programming data set. So where you clearly see that except for one case, Reflexion is doing a really good job. Okay? So to summarize, Reflexion also iteratively improves, but it uses tools and LLMs for reflection rather than just LLMs. That's the only difference. Again, it can be combined with React. So before we wrap up, this is one of this particular paradigm has not yet caught up big time, okay, but it seems like is a right direction to go for the time being, because typically these React, Reflection, all of these, when you interact with say software engineering agent and the compiler gives you error logs or the code execution logs, all these are extremely long, right? And every time you fail, you're going to keep redoing it again and again and again, and the logs are going to get bigger and bigger and bigger. And because the logs got so big, right, it might lose track of where it was to begin with, right? And it's extremely expensive also. So people have started to think about how do we sort of reduce this context window, right? And for that, this sort of is like an obvious plan, which is like first create a plan of what all you need to do and execute them separately, right? So, but creating the plan together is the main difference, because in React, typically you have an idea of what is to be solved, but then you always think through the first step, execute it, get the observation, and then once it's done, you go to the next step. So you go step by step, and the whole reasoning and logs get appended every time, right? So here, all they are saying is that you can split the plan into multiple chunks and then work through them. So typically now people use a combination of the two in real world applications, mainly because there are a lot of cases where you would use tools. There are a lot of cases where you would use LLMs. This will sort of help to plan well, right? If you have 7 or like in the previous lecture, we talked about functions and tool callings. If you have a bunch of functions and tools available with you, so when you create an initial plan, a very detailed initial plan, you got to get a sense of what all tools can be used where there is a gap, where LLMs can fit in, and things like that. For example, if you pose a questions like get me the top 5 talked about companies on Twitter, and then whether in the last month their stock price went up or went down, right? You may have a tool that converts a company name to the code, and you may have a tool that gets you the stock price for each code, right? These two tools you may have, but you might have to search Twitter or search the web to figure out what is more popular, and you may have to also have to get some notion of what was the stock price a month before, what is it now. So if you have a lot of tools that can let you do most of these tasks, and you can easily figure out where LLMs fit into picture, where search fits into picture. You can also use a matplotlib Python script to generate a nice graph. So you can have a lot of these tools readily available for the LLM, and then you can create a plan and let them execute in certain way. In this paper, what they say is that you create a plan, you execute them if needed in parallel, and then get all the outputs together, and then stitch and then generate the response. So this way you don't plug in the output of each module before you run the next one, right? So basically you will end up saving token space and the amount of money you spend. But it's still at a very early stage, but it looks like the most obvious choice is mixing the both, React and Revu together. Revu is more like I'll split it, and then I'll do it, and then I'll join them. React is like I'll go one step at a time. If there is any failure, I'll go. But here, if there is any failure, it's going to be a messy thing, right? Because if second module failed, and if you have output for 3 and 4, anyway you can't do much with it, right? Yeah. So this is this part is what is a lot appealing for people, because you can use, like, designing a React system requires a lot of effort, right? But designing just the planner may not be as difficult as designing the whole React thingy, right? Because in React, you have to create a real life trajectory. Oh, it hits that API, and the API is going to give me error message, right? If I get an error message, then I should act like this. So you will actually need a combination of real life plus simulated scenarios to really create a good React in context example, right? But in case of, if you have an LLM that does reasonable planning, then this solves it, right? Like your planner can be like an LLM, like Llama 8 billion model or Llama 70 billion model, which you can only train it to do plans, right? So this sort of helps you break down the task a little bit. So people here are saying that if each of my worker is failing, then I will do React within that worker, right? So there are a lot of things you can do, but it looks like the main advantage of this framework is just at having the LLM as a planner separately, so that you can fine tune it for general purpose planning, where tools can also be used and LLMs can also be used. So this was one nice paper that came out late last year, which basically said that there are a lot of models in Hugging Face, and typically each models have their own strengths. Some models are good at language, some models are good at speech to text, some models are good at image captioning, some models are good at image generation, right? But if you have to do a task which requires most of them together, then one way is to wait for multimodal LLM to become good and accessible, right? But the other way is like we can just stitch things together with what we have, right? So that's what these guys did. One of the example here is like, please generate an image where a girl is reading a book and her pose is same as a boy in the image example.jpg. Then please describe the new image with your voice, right? So basically you'll have to figure out this part because the input here is this example.jpg image along with this whole description, right? So here you first have to figure out what is the pose of that boy, right? Because her pose is same as the boy in the image. So you have to create a girl who's reading a book with a pose, and that pose should be same as the boy, right? And then once you create the image of the girl reading the book with the same pose, then you'll have to create a caption for it, and then you have to use voice to convey that caption. That's the goal here, right? So the model is able to figure out. So this is like Revu, right? This is exactly Revu, where it tells I need one of the tools which is pose detection, and then I need a tool for pose to image because I have to create the image of the girl, and then I need to figure out how to read that image that I created with the girl, and then how to create a caption for that image, and then finally how to use voice to convey that caption, right? So it's also created a dependency graph, right? So now all it has to do is execute this one at a time, and then finally once it executes, then it can generate the final response, which is the audio. So here you see this is the image of the boy, and then it uses pose detection to get the exact pose of the boy, and then it was able to generate an image in which a girl is reading in the exact same pose, right? And then it used an object detection module to figure out what all objects are there, and then an image caption module to figure out a girl is sitting on a bed reading a book, right? And I don't know if that's a bed or not, but still it looks like a bed. But then finally you can use text to speech module to speak it out, right? So yeah, so that's the summary of all the techniques that we've seen today. The Rewu technique sort of decouples reasoning from observations, right? You reason everything together, have a good plan in mind, and then if in a certain module your observations are not as expected, then just work on that part, right? So don't sort of mix the whole thing, and if the second module fails, then the third and fourth module will have so much context, unnecessary context in them, right? That is going to waste your token space. So you could save that, and that thereby reducing the token consumption and execution time, right? So before we sort of wrap up this discussion, I just wanted to bring to your attention another sort of paradigm that people are working on. So currently, whatever we talked about all falls under an individual agent setup, including the SWE agent, right? So where you get a task at hand, you would get an output, or you get an action, and then you execute the action, get some reflection, and then keep doing it until you get the final output. That's what we've seen so far, right, in different ways. But what they decided is that, like, look, the important point to note here is that the prompt that generates the input is not the same prompt that's going to reflect, right? So like changing the prompt and making them specific is actually helping the model a lot, right? And the communication between the two is improving iteratively, is improving the performance of the output. So they've taken this to another level of abstraction. What they're saying is create a persona called tester, right? Create a persona called developer, and treat each of these persona as an agent, right? And create agentic solutions for them, right? So in general, you could sort of have a separate, like, let's say that you are creating an online painter, so you need to get some inspiration for something. Let's say, like, somebody says that paint me an image of a beach or something, right? So you could always search, get different, get to understand how beach looks like, right? And then also figure out different painting styles that would go well with it, and then you can search. So the search agent then sort of gives you a lot of ideas on how to like paint the beach, right? That can be decoupled from the actual job of painting, right? So it can reflect on itself, figure out how, like, maybe it has a criteria about how people like what type of images and things like that. So a very focused job, the search agent can give you some description about what is to be painted in what style, what brush strokes, what things like that, and then you can give it to a painting agent, which can just paint and give you back the output, right? Because it's better not to overload your LLMs, because the lesser precise instructions you give, the more likely it is to follow, right? And similarly, you can also simulate a scenario where a human agent is discussing with one interface, and this agent in turn has a separate bot that mimics Socrates or Confucius or Aristotle, right? So it can get views of Socrates, Confucius, and Aristotle together, and then it can create some sort of a more abstract notion of what this is. This sort of approach sort of gives a lot more character and style, and sort of disentangling things together, things differently, will give you a lot more very clear instruction following models, right? So multi-agents are sort of like the trending topic now. Now there is not, people see potential, but there is a long way to go. Thank you.